Okay. We started into Franklin's theory of electricity last time that he developed in order to physically explain the results of all these experiments that people had been doing for decades at this point. And I listed a number of basic points in Franklin's theory last time. First, Franklin assumes that all bodies have an electrical fluid in them. And when bodies don't exhibit any electrical properties, as most bodies don't, that just means they have the normal amount of electrical fluid. If they have more than that, Franklin says they're electrically charged positively. And he assumes that glass is charged positively. And we know that amber has a different kind of electricity than glass, so amber must have a deficiency of this electrical fluid after you rub it. And so so amber would be charged negatively. Now, Franklin, there was something that was, well, let me first just review a couple of more aspects of the theory that we saw last time. See, starting with, by means of this electric fluid, in conjunction with ordinary matter. Okay, so all bodies are a combination of two things, this electrical fluid and the ordinary matter. Now, Franklin can explain all the results that people have seen up to this time by assuming that all electrical fluid repels all other electrical fluid, right? And that ordinary matter repels other ordinary matter. Now, all these forces are balanced when you have just the right amount of electrical fluid, but they get out of balance if you have more than that normal amount or less than that normal amount. And that explains all the attractions and repulsions that people have seen so far. And we went over last time exactly how it explained, for instance, electrification by influence. Now, one thing that is implied in Franklin's theory that nobody had said before is that electrical charge is conserved. Okay, that it always stays the same. See, Franklin is assuming throughout this theory that all that happens when one body, say, electrifies another body is that there's just a transfer of this fluid from between the two bodies, okay? Now, there's never a case where electrical fluid is created or destroyed. All it does is transfer between bodies, flow between bodies. It moves around from one body to another, but there's always the same amount, total same amount of this electrical fluid. Now, contrast that with heat, for instance. I mean, two things happen. If you take a tube of glass and you rub it with a cloth, okay, you electrify it, but you also heat it up, right? Now, is heat conserved in that case? No, it's not, right? Troy's shaking his head. It's generated. I mean, we're generating heat when you rub the cloth against the glass tube. Now, presumably, I mean, electricity could have been, you know, the same way. Maybe the rubbing actually generates electricity. That's, a lot of people thought that before Franklin. But Franklin's taking the opposite view. In his theory, the electricity is never being generated. It's just being moved around. Troy.
But then how would his theory explain how electricity leaks off, like when if you don't have a Leyden jar, just like we do?
Oh yeah.
How to explain that?
Right. Well, I mean, people had noticed that in cases where, let's say, you charged up a glass tube and put it on a wooden table. Okay, wood's an insulator. and just left it there, the electricity would leak off the tube. Okay. But it leaked off faster on humid days, okay, when there was more water in the air. So people realized, aha, the water must be carrying away the electricity. So it's still not a case, that's what Franklin would say. It's not a case where the electricity is disappearing. It's a case where the electricity is being carried away by the water in the air. Okay, so the first one of the first results that comes out of Franklin's theory is the principle of electric charge conservation. And what that means is that the amount of electric charge let's make this even more explicit. The total amount of charge is always the same. Electric charge is merely transferred between bodies. It can move from one body to another, but the total amount always stays the same. And everybody has this electrical fluid in it, even when it's not, when it doesn't exert electrical forces on other objects. That when it doesn't exert electrical forces, that just means it has the normal amount of fluid. Okay, now let's think about how Franklin would explain the operation of the Leyden jar. So let's go back to the Leyden jar and test our understanding of Franklin's theory. Has everybody got that? Everybody's got the principle of charge conservation? Okay, so let's, we have our, say, glass jug here. And, I don't know, let's say we have a mercury in our jug. And then on the outside, we've coated, so we have I'll go ahead and draw in the thickness of the glass here. And then on the outside, we have a metal coating. I don't know, let's make it silver. And then this is our wire, and we're going to charge up our big glass sphere here by spinning it around rapidly and holding various small animals up to it. And so what happens now in this case? What's going on in terms of Franklin's theory? Evan.
The electrical fluid is building up on the glass sphere and then
Okay, so let's just stop there for a second. So if we've got, say, some animal fur that we're holding against this glass while we're spinning it around really fast. Yeah, your cat, okay. What happens, what is happening between the cat and the glass sphere?
The cat has electricity being transferred to the glass sphere.
Absolutely. The cat starts out with a normal amount of electrical fluid, according to Franklin. So does the glass sphere. But what happens when you spin this glass sphere around and hold them together is that part of the electrical fluid that was in the cat fur is being transferred to the glass sphere now.
And so they just, is that why they puff up, I guess? Is that
Hmm?
why they thought the cat's puffed up if you put in the air the glass sphere?
Well, yeah, the cat's fur will actually stand up a little bit, right? Because now what's happening with the cat? If the glass has excess electrical fluid, the cat has a deficiency, right? Because it got its extra electrical fluid from the cat. So the cat's going to end up electrified too. Okay. But we end up with this excess electrical fluid on the glass sphere, so it's positive, according to Franklin. Now, what happens when we touch the wire to it?
The excess is traveling through the wire into the mercury, making the mercury.
Exactly.
Yeah.
Exactly. So now you have the wire will take the excess electrical fluid off the glass sphere, and now it's in the mercury. And we can continue this process. You know, after we touch the wire to the glass sphere, we can repeat the whole thing. Hold the cat up again, do the whole thing again, and keep putting more and more electricity into the mercury in the Leyden jar.
If you touch the cat, would negative electricity run through, like?
Yeah, if the wire, instead of being touched to the glass, was
It would be all negative.
was touched to the cat, right? Then you would end up with negative,
But what
right?
happens if you've charged up the jar a whole lot with all sorts of, with a lot of positive?
Yeah.
And you just touch it once to the cat, does all of the charge in there go negative, or?
Oh, if you have a whole lot of positive in here, and then you touch the wire to
Cat once.
the cat, and the cat's charged up negative,
Would they balance?
and the cat, I take it, is on a insulating material, because if he's not, he's going to get zapped. Okay, so we're not zapping the cat. Well, what would happen is that some of this electricity would run out onto the cat, so the cat became neutral again. But then, presumably, you have more of electricity in here than you have on the cat. So as soon as the cat becomes neutral, then the electricity stops. The rest of the electricity would stay in the jar. Selah?
What if you used a bald or shaved cat?
Oh, that's not a serious question. A bald
I was
cat?
just wondering
A bald
if
cat
it's
wouldn't
bald.
work very well. Troy?
But wouldn't it charge the cat to be positive with the jar? Like, wouldn't the cat become positive as well?
Oh,
since there's more positive than
Actually, not. I'll show you why. I haven't finished explaining the Leyden jar here yet. So let's go on. Now, there's one part of this we haven't explained at all yet, and that is why is it important to coat the outside of this Leyden jar with a conducting material like silver? I mean, what's the point of the silver here?
Because you're supposed to hold it, right, with your hand.
Right. Well, you could, yeah.
Or does it have, or does it make any difference with your hand, or if it's placed on something at all?
Well, let's say that we're either holding it with our hand or we've got a little wire here that's attached to the ground or something. Okay. Now, but what is the function of this silver? What would happen to, in this case that I've just drawn here? You've got this conducting material here. Now you've filled up this jar with all these positive charges. What is the electric charge going to be on this silver out here?
Because
Is it going to be neutral?
It's separated by the. Wait, this is a glass jar?
Oh yeah, it hasn't touched any of the conducting material inside the jar.
Yeah, so it's separated. So would you?
Right, it is separated, but remember that electrical fluid repels other electrical fluid, right?
That means
Oh,
silver
so
would have
that
to be
silver's
negative.
being pressured.
So if all this excess electrical fluid in the mercury is repelling other electrical fluid, and that fluid, because silver is a conductor, that fluid is free to move, right? That's what it means to be a conductor, that the electrical fluid in the body is free to move around.
All the electrical fluid is buzzing around in the silver.
So, well, the electrical fluid in the silver will
Be repelled.
be repelled, will want to get away from this jar, right?
So it'll run off.
So, if you
So
put
it's going to run off into the ground,
Or onto you.
or onto you if you're holding it.
so then it'll become electrified.
So it's going to have a deficiency of electrical fluid, making it negative. Now, once it becomes negative, okay, so a lot of electrical fluid has been driven out of this silver, leaving.
How come there isn't?
Oh.
How come all of it doesn't come out? Because if the mercury is still pressuring it, no matter how.
Well, I mean, we don't. If you could do an experiment that would prove that once you get to a certain point, no more electricity can be driven out of the silver, then Franklin would conclude, well, you've driven it all out. Okay, but he never got. He never did an experiment that showed he could get to that point. Troy.
But couldn't you just make an electroscope that can measure the amount of electricity that it has?
We're going to get to that in a minute.
'Cause,
How would you do that, though? I mean, do you have an idea?
yeah,
Okay.
like you'd have 2 pieces of gold foil, like
Yeah.
hanging, and then you have like, let's say, a glass ball or something on the top.
Yeah.
And if you like held an electrified object close to it, then it would make the golden fleece become like positively or negatively charged,
Yeah.
and then they would separate like that.
Did you think that up? Or did you read about
I
that?
read about it.
Oh, okay. That's a really good idea. People do try that. I'm going to get to that maybe later today, probably on Thursday. And we'll talk about exactly what people could learn and what they couldn't learn when they did that. Okay, so getting back to this, the Leyden jar now. The electrical fluid, the excess electrical fluid in here, drives the electrical fluid out of this silver here. Now what's left, well what's left in the silver? Evan?
More matter.
Yeah, just the ordinary matter stuff. Okay? Now, what what is the effect of that ordinary matter on the electrical fluid?
Isn't it being attracted?
Yeah, ordinary matter attracts electrical fluid.
So there,
Okay, so the silver now is actually serving a very important function here, because as you put the excess electrical fluid in the jar, it drives the electrical fluid out of the metal that's coating the outside, but it leaves ordinary matter that attracts that electrical fluid and holds it in the jar. Okay, Nick.
Wait, I forgot what I was gonna say.
Oh, okay. Troy?
Can the ordinary matter move, or does it always just stay fixed in Franklin's theory?
Oh, in a solid, it just stays fixed.
Okay.
I mean, you know, obviously in a liquid, it can move around. Tom?
Do you have to disconnect the ground wire for the silver to hold it in? Otherwise, the electricity could just run back up through the wire back into the silver.
Oh, but it won't do that because it's being repelled by the mercury. So, yeah, I mean, if you don't have this ground wire,
and it's not making any difference.
then what, so you won't really be able to charge up your Leyden jar because you'll start putting electricity in, but then it will be repelled by the electrical fluid here, and you won't be able to get much into your Leyden jar, right? But if you have this ground wire, then as you put electricity in the jar, it drives the electricity out from the conductor on the outside, and then that ordinary matter helps hold the electricity in the jar. Troy?
Would it help to put another insulator and then another conductor around it, or would that just do nothing?
Oh, well, I mean, it would basically, if you had a way of charging that
Middle.
other surface, you would just have a double Leyden jar. I mean, you could make Leyden. You basically you could build a Leyden jar inside a Leyden jar if that's what you mean. Sure, that's possible. Yeah.
How does it help to have a conductor inside the jar as well? Like,
Oh.
you say,
Well, the charges in a conductor are free to move around.
yeah.
And, well, actually, that's a good question because part of my diagram here is a little bit misleading. So let me fix it. Yeah, Nick.
Well, they said the ordinary matter becomes more than the charge, right? If you have a deficiency of the charge, then the ordinary matter becomes more. Or does
Oh,
it
no, it stays the same amount of ordinary matter, but the ordinary matter, see, between two uncharged bodies, you've got ordinary matter in each and electrical fluid in each. And there's a delicate balancing of forces here because the electrical fluid in this one is repelling the electrical fluid in this one, but the ordinary matter is attracting the electrical fluids, and so they balance out. I'm not sure, maybe I didn't get your question.
Does the ordinary matter, the amount of ordinary matter, change?
No, the ordinary matter, Franklin assumes that the ordinary matter is conserved too. I mean, you can move it around, but it always stays the same amount. So it's just like the electrical fluid in that way. Now, I mentioned that the electrical fluid that you've put in this jar is attracted now to the ordinary matter on the outside, and of course not repelled by the electrical fluid that used to be in the silver isn't there anymore to repel it. So what's going to happen with these charges? I mean, are they just going to swim around randomly in this mercury? Troy?
They'll go to the outside of the jar.
Exactly.
Stay around the outside.
Yep.
How will they get to the outside?
Well, that's the advantage of being of a conductor. That's what Troy asked about. Why do you have to have mercury in here? Why do you have to have a conductor? Well, so the charges are free to move around. And when they're free to move around, they can move to the outside here and pile up on the inner surface of the jar, and then where they're attracted to the silver on the outside surface of the jar.
So they can.
So that's actually what's going on here. I mean, this is the actual. It's not like you're filling the whole jar up with electricity. You really aren't. All the electricity you're putting into this jar just piles up on the edges.
Is there any way that you can make it so that it is like all electricity?
Yeah, if you fill it up
Like
so much,
just
that
keep on until it's all around the edges technically?
and it's also in the middle too.
Yeah, no, you can't. Turns out you can do that to your heart's content, and you will not be able to get charges to stay in the middle of this jar. There's later people will discover why that is, but you're not going to be able to keep charges in the middle. They're all going to go to the edges. First, actually, you can see one of the reasons why that's true from what I've already told you.
Because the silver's attracting it.
Well, remember, electrical fluid. Well, no, I shouldn't say that. Let me skip that. Nick.
Well, supposing like the earliest Leyden jar when they didn't know that silver should be coated on the outside,
Yeah.
would the electricity still be on the outside because there's no negative charge on the outside that
Yeah, but remember, okay, there they were holding the jar. That's the only reason it worked. Okay, they didn't know yet to coat the outside of the jar, but they were holding it. And so the hand was the conductor. And charges were piling up on the hand. Evan.
Did Franklin's theory include why some objects were conductors and some were insulators?
Oh, why? No, I mean in terms of analyzing the materials.
Yeah, or
And
why it would
I mean, the only thing Franklin could say is there is this difference between materials, that the electrical fluid moves easily through some and not through others. And right now we don't know exactly why that is, but it is. It would be much later before people understood enough about these materials to actually understand their electrical properties. And in fact, at this stage, I should mention, we're going to talk about this later in the year, but Franklin's doing this work in the late 1740s. Well, there is no science of chemistry in the late 1740s. We'll see later that chemistry really gets started, I mean, as a real science in the next few decades after Franklin. So,
Had he had chemistry, would Franklin have gone much farther in his experiment?
no, because actually you need a fair amount, you need to know a lot about chemistry before you can start making the connection to electricity and actually understanding the electrical properties of materials. That wouldn't actually happen for another century after Franklin. Troy.
Would the jar like explode if it got too much electricity in it from the pressure, like that they're attracting each other?
No, because, you mean,
Like wow.
is there such strong attractive force between the the positive electricity on the inside of the glass and the negative on the outside, that it could crush the glass? No. No. We're safe there. You'd have to have a lot of electricity for that.
Is it
Okay.
possible or not possible, though?
Oh, it's possible to crush things with electrical forces, certainly. I mean, if I mean, you can. I mean, the kind of. I mean, not by holding a cat against a spinning glass sphere, though. I mean, you need something. You need a more sophisticated equipment than that. Okay, so everybody understands how Franklin's theory accounts for the Leyden jar now. Okay. Now you see, one of the questions that came up before was, well, what if we had a huge Leyden jar and we had water in here? Could we jump in and swim around and not get electrocuted? And I said, sure. Well, you can see why now, right? I mean, all the charges are just piled up along the edges, and you're swimming around in this pool. You're not even, and there's no, you're not touching. I mean, the only time you get electricity running through you is when you're in the circuit. I mean, the reason that when von Kleist first got shocked, what did he do? He filled up the Leyden jar, and while he was holding it in this hand, he touched this wire.
So the negatives and the positives.
Okay, so what happened to von Kleist? Yeah, he got a big shock, but
Positives and the negatives.
where did the electricity go? Okay, according to all the excess electrical fluid in here went up this wire into von Kleist's hand, traveled through his arm, through his body, and to his other hand, and flowed into the silver that has a deficiency of electricity out on the outside of this jar. I mean, if you were holding this jar. So basically, all the excess electricity in here, balanced by this deficiency of electricity outside, was that whole situation returned to equilibrium very quickly through von Kleist. Okay, Troy.
So if there was a big enough charge, it would have made both of his arms numb?
Yeah, I mean, that's what he complained about, was that the shock stunned his arms and shoulders. And you can see why he described it that way. I mean, the electricity went right through his arms and shoulders.
What you said that only his right arm got a huge numbness.
Oh, I can't. Maybe he did remember it more in one arm than the other, but it did run through. It had to run through from one hand all the way to the other. Okay. All right, now let's start into Franklin's next major accomplishment. So we've covered what I think is Franklin's probably most significant achievement, which is coming up with a theory to explain all these experiments that we've been talking about. But the next thing he does, which he's actually more famous for, is his famous kite experiment, right? Now, Franklin is picking up on some experiments that Stephen Gray initially did here. Remember that Gray had made this comment about a connection between electrical sparks and the noise they make and the way they look, and lightning and the way it looks and the noise it makes. And just pointed out that there was a similarity between these two. It's like the electrical sparks are like lightning, only on, of course, a much, much smaller scale. And Franklin knew one other thing, that that people had, that you could, well, Gray initially had another experiment in which if you charged up an object, say, so it's got charges all over it, and then you held a pointed metal object up to it, you could draw sparks from it at a pretty good distance. You remember I told you that Gray tried, say a blunt metal object, and found that he had to bring that, much closer in order to draw electricity off of his charged body. But a pointed metal object could draw the electricity off this this charged body at a distance, say, of 6 inches, where maybe he needed to be within 1 inch, with his blunt metal object. So Gray had discovered that pointed metal objects were effective at drawing electricity off of strongly charged objects, even at a distance. And Gray had made this interesting observation about the similarity between lightning and sparks, electrical discharges. So Franklin puts those two things together and gives him an idea. See, he wants to test whether or not these, whether lightning really is an electrical discharge, right? Whether these thunderclouds are really strongly electrically charged, and that's what's causing the lightning. Well, Franklin figures maybe he can draw the electricity off of these thunderclouds if he gets a sharp metal object up close to them. Now, one thing, now one other point to keep in mind, and I wanted to mention. I think one of the reasons that Franklin is the first to take this idea seriously and do this experiment, rather than the other people that might have noticed some similarity between electrical sparks and lightning, is because of Franklin's theory, what we just talked about. See, on Franklin's theory, up till this time, a lot of people have thought of electricity just as a small force that affects certain objects when you rub them. Okay? And no one thought of associating it with something huge and powerful like lightning. But on Franklin's theory, notice everything has this electrical fluid. I mean, this is throughout all bodies. And all you need is an imbalance, some deviation between the normal amount of electrical fluid, either an excess or a deficiency. And if that deviation gets big enough, you should be able to have huge electrical forces. See, Franklin's theory inclines him to think that maybe electrical forces could be huge and powerful. Nobody thought of them that way before Franklin. But it's a natural outcome of his theory that, maybe when we're rubbing amber or glass, all we're doing is transferring a very small amount of this electrical fluid from one body to another and causing a slight electrical charge. But maybe there are cases when you can have huge buildups of this electrical fluid or huge deficiencies, and they can cause enormous forces. Well, that's Franklin's idea on lightning. So you can see that you know, it's a long way to go from seeing a little spark from a piece of amber to associating that force with something that can split an oak tree, right? But Franklin's theory makes it more plausible. Nick?
Didn't he also want to like figure out lightning because he was part of like this some kind of fire thing because it kept on setting Faust on fire at the time?
Oh, yeah. I mean, there was a problem, obviously, when lightning hit somebody's house, and Franklin did figure out how to deal with that. And I'll get to that, and right after I describe his kite experiment.
Do like a metal roof or something.
Yeah, well, I can tell it to you now. I mean, Franklin is known as the inventor of the lightning rod. Okay, he figured out that if you put a big metal pole up, say you run a big sharp metal pole up the side of your chimney and have it sticking out above your house, well, and into the ground, well, the lightning will hit that pole, and the pole will carry the electricity away into the ground, and your house won't be damaged. You know, without the pole, if the lightning just hits your roof, you're in trouble. So people could protect their houses with these large, long, pointy-ended conducting poles. Okay, so Franklin has this idea of putting a pointed metal object on a kite, and in a thunderstorm, flying this kite up so it gets close to a thundercloud. And of course, the fact that it's raining helps him because that makes the kite string conduct electricity better. And we'll, now Franklin, I'm down to my last minute here, but Franklin, how is he going to protect himself, though? Is he just going to stand there holding the kite string out in the rain?
By having a metal object on the string. By having a metal object on the string?
Yeah. First he ties a key to the end of his kite string. Then, I mean, does he just figure the key is going to save him and hold the string? No, he's not that dumb. He ties a silk cord to the string, and he basically hides under a shed, so he's dry and his silk cord is dry. And so he did take some precautions, and he did live through this experiment, which is the important thing about science experiments. He didn't, but I'll finish this story next time. There was a guy who tried to repeat this experiment and did manage to kill himself.